Alright, hi everyone, we're back and we're gonna continue now to contribute the Dino V2 model to Hugging Face. And so we've already finished those first 5 steps here. So the last thing we were doing was implementing the model test. So one thing I will do, and that you will probably also need to do regularly when you're working on a separate branch on GitHub, is you will need to rebase on the main branch of Hugging Face. So basically what I'm doing here is I'm fetching the latest commits that are happening on the upstream remote. So remember, if you type git remote v, you see which remote repositories you are referring to on GitHub. So in this case, we have the upstream remote, which is referring to the official Hugging Face Transformers repository, and then we have the origin remote repository, which is referring to our fork. So this is our fork of the Hugging Face Transformers library. And so typically when I commit, then I do git push origin and then the name of my branch. If you just push to my fork and not push directly to Hugging Face Transformers. But so now what we've done is we've done git fetch upstream, which will fetch the latest commits here from the main branch of Hugging Face. So the ones that are present here. So the latest commit, for example, here was 3 days ago. And then the next thing you will need to do is git rebase upstream -main. And this will basically place all of our commits of our Dino V2 branch on top of the main branch of Hugging Face Transformers. So as you can see, there is one conflict. So then you need to basically make sure that all of those conflicts are resolved. So in this case, for example, there was an update on the image classification markdown file. And that's probably because there was a new model being merged recently. And I think it was the mobile VIT V2 model. Mobile VIT. Yeah, as you can see, this one includes the new mobile VIT V2 model, and whereas this one doesn't. So then you always need to accept either the green or the blue one, the current change or the incoming change. In this case, we need to accept the current one. Then we need to hit save, and then we need to stage this. So staging is the same thing as doing git add, and then, for example, all of your files. And then next you can do git rebase -- continue to continue rebasing. So again, see, referring to this conflict, I think we again need to accept the current, hit save, stage them, and then do git rebase continue, and then we have successfully rebased. So now if you type git log, you will see that we are seeing our latest commits, but now those are placed on top of the latest commits here of the main branch. So this basically makes sure that we are in sync again with the latest changes that are happening on the Hugging Face Transformers repository, and that we don't have any merge conflicts. And so the last thing we did, that was actually step number 5 here, was implementing the model test. So let's see again whether these run fine. So for that, I'm gonna go here to the test folder, then to the models folder, and then to Dino V2. Then you can, for example, type run slow equals yes, pytest, and then a path to those test file. And remember that in the Dino V2 model test class, we are overriding, or we are inheriting from the model tester mixin class, which basically defines a lot of the common tests that are shared between all of the models, and those are defined here in test modeling common. And so as you can see, we are running quite a lot of tests, 80 in total. And so some of them are marked with a slow annotation, which means that they are slower than the regular ones. So in this case, it's only complaining about the test model from pre-trained tests, so you can actually type them here. Well, I think this one is not inherited, it's just defined here, so it's So it's a slow test, and basically it fetches this list here, the Dino V2 pre-trained model archive list, and then it just checks whether we can instantiate a Dino V2 model from the repositories that are listed. And this one is imported from the modeling file. So if you go here to transformers, models, Dino V2, modeling Dino V2, you will see that here we define a Facebook, but this one doesn't exist for the moment. Currently there's only actually a repository under my personal name, so we will have to transfer that one to the Facebook organization, and then this test will pass. Alright, so we've finished basically the fifth step here, so we can move on to implementing the preprocessor. So in terms of the preprocessor, well, it depends of course on what kind of model you're adding to the Hugging Face Transformers library. Is it a text model, like the BERT model, for example, which is of course one of the most used models within Hugging Face. So for that, for text models, you will have to implement a tokenizer. So a tokenizer can be used to turn text into those input IDs, which are like the expected inputs for the model in case you're contributing a text model. So if you look into how that's implemented, let's go to the BERT folder here. You can see that we have a tokenization BERT.py file and a tokenization BERT fast.py file. So yeah, for tokenizers, there's actually a distinction between slow Python-based tokenizers, which are implemented like in this file. And then we also have a fast implementation, which is based on a Rust implementation that is actually in a separate tokenizers library. And then there's like a Python wrapper on top of that. So maybe, yeah, in terms of implementing the preprocessor, well, that depends on the model you're contributing. So yeah, it could be a tokenizer in the case of a text model. And in that case, actually, you need to implement both a slow tokenization underscore BERT.py file, for example, which in that case needs to inherit from the pre-trained tokenizer class, as well as a fast tokenizer, which is backed by the tokenizers library. And this one is going to be a lot faster as it's written in Rust in the backend. This one needs to inherit from pre-trained tokenizer fast. So that's in case of a text model. However, in our case, we're contributing a vision model. So in that case, you need to implement an image processor. So let's, for example, go to the vision transformer model, or let's go to the SWIN transformer model. Well, this one, as you can see, it doesn't have a image processor class, and you might wonder why that's the case. Well, actually, the reason for that is that sometimes we have models that actually use the same exact preprocessor class as an existing model in the library. In that case, there's actually no need to add a new image processor class, but for example, if we go to the vision transformer class, I'm not sure why it's so slow here. Maybe in the meantime, let's just go over the files here locally. If we check the vision transformer, you can see that there is an image processing vit.py class, and this one inherits from base image processor. So maybe to make this a bit more clear, so in case of a text model, implement a slow Python-based tokenizer and a fast Rust-based tokenizer class. In case of a vision model, implement a image processor class. And so yeah, for example, for the vision transformer, a VIT image processor class is defined, which inherits from base image processor. But then, as we saw for the SWIN transformer, which is another vision model, there's no image processor defined, and the reason for that is simply that SWIN's image processing is exactly the same as an existing model in the library. So then we need to go to the auto mapping folder, And then, for example, here there's image processing auto, and here you can find where Swin is mapping to. So in this case, for example, the Swin transformer uses the exact same pre-processing as the Vision transformer. So we just add a line here, and this will make sure that you can then do from transformers import auto image processor, and then you can do processor equals auto image processor dot from pre-trained, and then you can specify any Swin model from the hub. So let's go to one like this one. Well, this is actually a Swin v2. Let's maybe go to another one like this one. So if you just do this, it will work, and it will actually, if you check the type of that processor, it will be a instance of a VIT image processor. So yeah, that's where this mapping, this auto mapping comes from, and we actually have the same thing for classes, like model classes as well. So you can, for example, do from transformers import auto model for causal LM, and then you can just do this. And for example, say I want to load GPT-2, and then it will automatically map. So if you check here for GPT-2, it will actually automatically map to this class. So let's check that, as you can see. So yeah, the auto mapping is basically used to make it easier for users to just load in the right class without the user having to care about the exact name of the class, just by providing an ID of the model hub. So yeah, so maybe let's add some info here. So in case of a vision model, implement a image processor class inheriting from base image processor. And so here, in case of a text model, you need to implement a tokenizer or and a fast tokenizer class inheriting from pre-trained tokenizer. I think that was the name of it. Yeah, inheriting from pre-trained tokenizer and pre-trained tokenizer fast. In case of a vision model, yeah, you need to implement an image processor. And then there's also, of course, the case where you want to contribute a audio model. So actually I did contribute an audio model. That was the audio spectrogram transformer, also called AST for short. And in case of an audio model, the preprocessor class is called a feature extractor. So that's implemented here in the feature extraction audio spectrogram transformer.py class, and there you need to inherit from the sequence feature extractor class. So in case of a audio model, implement a feature extractor class inheriting from the sequence feature extractor class. Yeah, so this is an example of such a class. But then also, yeah, like lately there are more and more of these multi-model models coming out, which combine, for example, both the vision modality as well as text modalities. So that's a multi-model model. So in case of a multi-model model, well, actually for those kind of models, you will have to implement both the tokenizer, if it's using text, and then the image processor if it's using images as well as input. And then you need to implement, well, I would say implement a preprocessor class for each of the modalities, and then implement a processor class which combines them. So an example of a multi-model model that is quite popular is the clip model from OpenAI. And as you can see here, there is a tokenization clip.py file, a tokenization clip fast.py file. So both the slow and fast implementations of the tokenizer. There is also an image processor, as you can see here, which is inheriting from base image processor. And then there is also a processing class, which will simply combine them. So it wraps a clip image processor and a clip tokenizer into a single processor. And that's the class you will have to implement if you're implementing a multi-model model, because then you can use it to prepare both text and images, for example, for a model. And so we have more and more of these multi-model models. ClipSec is another one. But as you can see here, there's only a processing file defined, but not a image processor or a tokenizer. So that means that it's probably using existing classes. Like in this case, it's combining a VIT image processor and then a clip tokenizer or clip tokenizer fast. Another example of a multi-model model is the Wave2Vec2 model from Meta AI. So that's also implementing. So this one combines audio and text. So we need to implement a feature extractor class, Wave2Vec2 feature extractor. And then we need to implement a tokenizer because it's a speech to text model. So that's why there's also a tokenizer implemented here. And then we have the processing class or processor, which then combines them. So yeah, let's maybe illustrate that. If you, for example, load a clip processor from the hub, you can, for example, do the following. So you can specify a clip model from the hub, like this one. And then it will basically load the files for both the tokenizer and the image processor, and then you can actually check the attributes. So it has like both a image processor, which is an instance of clip image processor, as well as a tokenizer, which in this case it's loading the fast Rust-based tokenizer by default. And then again, we have the auto mapping for those classes. So if you go here to processing auto and then you search for clip, you can see that it will automatically map to a clip processor. So you can also do from transformers import auto processor and then do the following. And that then automatically will load a clip processor class. So that's a bit in short how pre-processing is implemented for the various models in Hugging Face. And so in our case, yeah, we're going for this case, of course, because we're implementing Dino V2, which is a vision model. So, well, actually, let's go maybe to the original repository here and see what the exact pre-processing is needed for this kind of model. It's, of course, very important that we have like the exact same pre-processing as the original implementation, because even for vision models, a super small difference like the interpolation that is used when resizing images can have a significant impact on the final performance of the model. So I'm gonna go here probably in the data folder, because yeah, there's where the data sets are defined when so they have a transforms. Well, actually we already saw this, right? We are already using this. So as you can see here, you can find what the exact same transformations are. So typically in Hugging Face transformers for vision models, well, actually for most of the modalities, also for text and audio, we just support the transformations that are needed at inference time. So when evaluating the model or when making new predictions, we're not supporting all the training transformations, because that would basically require us to like re-implement a lot of the stuff that is already implemented in other libraries like Torch Vision for vision or Torch Audio for audio. So we want to actually just provide the minimal transformations required for inference. So in this case, it's just first doing a resize. And yeah, in this is from Torch Vision. So the Torch Vision Transforms package is a really great package for preparing images for a neural network. And so the resize method here, if you only provide an integer to it, it will actually only resize the smaller edge. Well, the smaller edge of the image will be matched to this number, and then the image will be rescaled to this size. So that's what they're doing here. They're only providing an integer to the resize method, which means that only the smaller edge of the image will have this number. So that means that we still don't have a square image. So then, and that's why they have a center crop after that. So let's go back to the docs here, center crop. Then it will actually make sure that the image is a square. And then it's converting to a tensor, because here we're still operating, I think, on Pillow images. Pillow is, of course, one of the most widely used libraries in Python for working with images. So then we're converting to a PyTorch tensor, and then we normalize the image using the ImageNet mean and standard deviation. So it seems like a fairly basic image processing step, I would say, that I've seen already in a lot of cases. I think for this particular model, there's probably no need to implement this in a new processing class, because there's probably already a model in the library that does the exact same transformations, which are resizing the smaller edge first and then doing a center crop. So for that, I'm going to search for a setting do center crop, because yeah, typically the image processors in Hugging Face transformers, they have, for example, a do resize attribute and a do center crop, for example, and a do resample. So this one, for example, the BIT model. So the BIT model is a model from Google. It's short for big transfer. It was like I would say the latest big work from Google before they released the Vision Transformer. So this one is still convolutional based. But this one seems to also use the exact same transformations, which means first a resize, shortest edge is also being used here, followed by a center crop, followed by a rescaling. The rescaling is actually the equivalent of this thing here, maybe to tensor. That's just converting the Pillow image or NumPy array to a tensor. And in that way, we'll also rescale the values from 0 until 255 to 0 and 1. And then the image mean and standard deviation do convert to red, green, blue. That's interesting. It's converting here by default to red, green, blue. That's maybe not something we need. But as you can see, like in image processor and Hugging Face transformers is fairly basic. We just need to implement a pre-process method, which takes in the images and then all of these settings here, and then we just do them one at a time. So we first resize, then we center crop, then we rescale the images, then we normalize them. And all of that is done on NumPy arrays. So you need to first convert them all to NumPy arrays, but for that already some methods are provided. So you can actually just import the toNumPy array here, this function from the image utils module. But so in this case, it looks like we can just reuse this BIT image processor class. So in that case, what we can do is just go to the image processing auto mapping and just add DynoV2 here. Let's see, it's not added yet. So I'm gonna add here the following. And then in our conversion script, when we are converting the DynoV2 weights here, I'm gonna import a BIT image processor class. And then I'm gonna, so here we are using like the original transformations. So let's call this that original pixel values, and then we're gonna also create the pixel values using our processor. Where the processor is just an instance of the BIT image processor. And then we're gonna add a assertion here to make sure, so torch.allClose pixel values and the original pixel values. So basically here we are first resizing 256 let me go back to the BIT image processor, because those settings are by default 224. Let me go here to the preprocess. It's, well, those are different settings, so then I think we will have to say here that the size, I think this needs to be a dictionary. So do resize equals true, size being the shortest edge, but this needs to be 256. Then we need to say do center crop equals true, but the rest is, I think, the same. And then let's also check the image mean and standard deviation. This one is using the ImageNet standard mean. Oh, no, it's actually using the OpenAI clip mean. So actually this is wrong here. Just gonna include that fix in my... But yeah, we don't need the OpenAI clip mean here. We need, so that's also defined. So yeah, here in this constant.py file, we define like the various means and standard deviations when preparing images for models. So in this case, we need the ImageNet default mean and the ImageNet default standard deviation. So do center crop is equals to true, crop size is 224. And then image mean default standard deviation, and those we can inherit them from transformers. Image utils import. Let's maybe check again. Do center or crop size also needs to be a dictionary. Yeah, the reason we chose dictionaries is because, yeah, sometimes it can be just shortest edge, sometimes it can be both the height and the width. But yeah, that looks fine to me. So let's maybe run a conversion script and let's see whether we are now having the exact same pixel values. So we are instantiating a BIT image processor here with those settings, which hopefully, and it's not passing, but maybe it could be that this is set to, but also, yeah, we do have a convert red, green, blue, still not passing. Oh, it can have to do with the interpolation. Let's go back to the Dino V2. Which interpolation are they using here for resizing? It's bicubic. Let's see what they are using here. Are they also using bicubic? Yes. It can have to do with this to convert red, green, blue thing. But it's still not passing. Let's maybe check out. Not sure whether this is maybe still too harsh. Let's go to the conversion scripts of this BIT model. Okay, here. Oh, wait, unsqueeze. Okay, we're adding an unsqueeze. Oh, wait. No, that's actually correct, because the image processor here is also by default adding a do center crop, do normalize. Wait, resize shortest edge to 256, then center cropping to 224. Then we are doing the do the rescale, but that's actually by default set to true, so that's not the issue. Do normalize is equals to true, but that's also by default of case. Then we're providing an image mean and standard deviation. Okay, the means are very close, but still not exactly the same. I wonder why that's the case. I'm gonna run the BIT conversion script and see whether that still passes. Maybe there is something that changed to the image processor class. Okay, that's still passing. Dim pixel values, pixel values. Yeah, the only thing we haven't added here yet is the resampling method. But the resampling was set to by how... Okay, yeah, it has to do with the resampling, because here we're not providing any resampling, so we're just using the default resampling of this method here, which, let's go back to the docs here. Resize, by default it's using bilinear interpolation, but in our case for DynoV2 the interpolation that they use is bicubic, and that's the reason why we don't get the same results. So here, well, they are using bicubic, and this by default is also using bicubic, so this is now probably gonna pass. Still not the case. Yeah, it's using bicubic here. Okay, for the moment I still don't really see why it's not returning the exact same pixel values, because we are first resizing the shoulder edge to 256. We're using the same exact interpolation, which is bicubic interpolation. Then we're center cropping to a square, which is also happening here. And then we're rescaling. And then we're normalizing. And I don't really know why it's working for the BIT model, but not. So in this conversion script, everything is working fine. So yeah. This also means that we don't get the exact same the exact same logits out of the model when we're using our image processor class. Wait. What did happen to our conversion script? Because now it's not. Did anything change here? Okay, we still need to figure out why exactly the image processor is not returning the exact same pixel values as the original implementation. And then I think we're nearly done, because if we can just reuse this image processor class here, there's no need to implement new model tests for it. So if you go, for example, to the VIT image processor class, the test file of that, as you can see here, we do implement these tests, so you can actually just copy paste this file and then adapt it to make sure that it also works for your specific image processor class. In this case, it has apparently changed something. Yeah, it may have to do with specific differences between Pillow and PyTorch, but still I would hope to make sure this passes. Add image processor to auto mapping. Yeah, this is because we have rebased on the main branch, so we now need to push with this flag, and this will basically overwrite the changes. So now that we've done this, I think we are ready to open APR here, so it's appearing, and then you can simply do compare and open a pull request. So then, well, maybe let's go back here. So in terms of assigning people to review, I'm not going to do that yet because it's still work in progress. But yeah, here you can find like the specific mentions of all the people you can tag when it's advised to not tag too many people, just the ones that are responsible for it. So here I'm gonna add to-dos. The main thing is make sure image processor returns the exact same pixel values, convert all remaining checkpoints. So we can confirm, actually I should better to call this convert Dino v2, and let's call it to Hugging Face because it's already PyTorch. So this is converting the base checkpoint because it's defaulting here to this one. We can also specify Dino v2 fit small. Well, that one is probably not supported yet. Yeah, maybe let's do that first. So in the case of a small vision transformer, of course the number of hidden layers and so on is different. Let's see where we can find this. So in models, vision transformer. So here we have the small one, which uses a different embedding dimension. So I would say config.hidden size. I think it's called hidden size here. Yeah, instead of 768, it needs to be 384. Then the depth, the number of layers is also 12, but the number of attention heads is 6. And MLP, that's the same thing. So that's probably the only things we need to change here. Let's see whether we can now convert this one properly. So it's loading the original checkpoint. Yeah, Actually, I'm not sure why we are checking this here, because we can just do also get like the original last hidden state from the model by forwarding the pixel values through it, and then we can just say last hidden state 0. So remember, if we go back here, the forward method just returns the forward features method, and this one returns a dictionary. Okay. XNorm CLS token, XNorm patch tokens. Okay, so I'm gonna do here and then we can compare this to the original outputs. Let's see whether this runs fine. So now we are actually converting, well, we are basically forwarding the pixel values. It could be that this original model has a head on top. Which is set to identity. Okay, so in that case it's returning this here. XNorm CLS token. Okay, so it's already returning that. So we can just remove all of this. And it's returning a assertion error. Oh, it actually needs to be like this.